I am John Gulliver, and I will introduce the seminar and our panel for today. This series of seminars is co-sponsored by the Water Resources Center and the St. Anthony Falls Laboratory, both of the University of Minnesota, and also by the Minnesota Pollution Control Agency. The funding for this seminar series comes from the Minnesota Stormwater Research Council, which distributes funds from cities, watershed districts, or organizations, and the Clean Water Council. Today is the conclusion of the Spring of Media. We previously had a talk from Bridget Ulrich on biochar, thank you, and from Andy Erickson on the performance of media for different types of amendments. Today, we will have a 6-person panel discussion where Bridget and Andy will be joined by 3 practitioners and 1 researcher. These individuals are Erin Anderson-Wenz, Vice President and Senior Water Resources Engineer, Barr Engineering Company; Megow, Environmental Engineer, Natural Water Resources Research Institute, University of Minnesota Duluth; Erik Megow, Senior Water Resources Engineer and Associate, Stantec; and Mike Isensee, Administrator of the Carnelian and Marine on St. Croix Watershed District. And then we also have Bridget Ulrich, Environmental Chemistry Research Program Leader of the Natural Resources Research Institute, University of Minnesota Duluth; and Andy Erickson, Research Manager, St. Anthony Falls Laboratory, Twin Cities, Minnesota. So we will first have a short overview on filtration media and amendments from each of our new panelists, with a couple of questions from in-house and online following each overview. Online participants, please put your questions in the Q&A box and vote on the ones that you are most interested in. So we'll start with Erin Anderson-Wenz. Okay.
Hi, good morning, everybody. Thanks for coming out. My name is Erin Anderson-Wenz, and I, as John said, I work with Barr Engineering Company. I have for 26 years, and I've been dabbling in filtration media for about the last 15 to 16 years. So have had a lot of adventures and learned a lot of things over the course of that time. And I've worked with a lot of you on some of the hardest questions. So it's really fun to be here today in person after such a long hiatus. So John, to advance slides, I just click here. Okay, great. So I'm gonna try to keep this short. But I do have a lot of things to share. I'll move as fast as I can. But what I want to tell you is that, you know, when we started out 15 years ago, my first big project in this realm was this one right here. This is an iron enhanced sand filter off of Beam Avenue in Maplewood, Minnesota. You've probably seen this filter. I think some people call it Stonehenge. I don't call it Stonehenge, but this is a project we did for Ramsey, Washington Metro Watershed District about 15 years ago. This was actually the first project that I signed the plans for. I had been a professional engineer for a few years before this, but this is the first one where my signature was going on the plan sheets. And I remember signing those sheets and thinking, gosh, I hope this works. It felt like a bit of a leap, although it was based off of a lot of research from Barr engineering staff like Keith Pilgrim and Brian Huser, but also research at SAFL and other practitioners. So we felt like we had a pretty good idea of whether it would work, and it did. It's been a really big success. And from that time, you know, we've been trying to find cost-effective, as simple as possible ways to treat particularly phosphorus. A lot of our clients, cities and watershed districts, are asking for phosphorus removal. Trying to find ways to do that. And when this filter went online and was successful, we thought, this is it. This is going to change everything. We can put these things all over the place, and they're going to be a silver bullet. And so I'm just going to cut to the chase. What I have learned over the last 15 years is, in terms of filtration media and most things in life, there really is no silver bullet. These are systems that need a lot of careful design. They need maintenance. They need monitoring during construction, and they need adaptive management. And so what I've really learned, if I tell you nothing else, just know there's no silver bullet here. We're not going to find something that works in all cases. So I just wanted to walk you through some of the evolution of my work with my colleagues at Barr And maybe some of it looks familiar to the things that you've been doing too, or the things you've been studying. So I mentioned that first iron enhanced sand filter on Beam Avenue in Maplewood. Andy refers to that one as the Minnesota filter. So I love that. So anyway, after that experience, we thought, well, let's try different implementations for this. So we did a big project in at Maplewood Mall, and we did a bunch of rain gardens in the parking lot there, and we put iron enhanced sand in as a strip down the middle of the rain gardens because they weren't good for infiltration. The soils were really compacted. So we did this application, and you can see when it grew in, you couldn't even really tell that it was a treatment cell at all. It just looked like a big, beautiful garden. That one's also been pretty successful and was heavily monitored for several years. Again, a Ramsey Washington Metro Watershed District project. There we go. Then we thought, well, how about clover leaves? I mean, that seems like dead space. How about we put iron enhanced sand filters in the clover leaves of highway interchanges? So this is at one of the lobes of the Highway 3661 interchange in the East Metro. So we have an iron enhanced sand filter there. This one's also done really well. And then we thought, okay, we've done some iron enhanced sand. And actually, by that time, we were learning that there's not every site is great for iron enhanced sand. And I'm sure we'll talk through some of that later today with the panel discussion. So we thought, what if we take a little break from iron enhanced sand and we try something else that doesn't have to deal with, we don't have to worry about oxygen. Like, it's so annoying. You have to worry about oxygenation for those iron enhanced sand filters. What if we do something that doesn't rely on that to remove phosphorus? So, and what if we tried to find a byproduct, like something we could put to beneficial use? So my colleague Keith Pilgrim started to look at spent lime, which is a byproduct of drinking water treatment. And so we started to put these filters in and had some early success. This is a small treatment cell in Ramsey Washington Watershed District, south of Wakefield Lake. And had some really great removals coming in off of just residential runoff through the spent lime filter, removing things like, yes, phosphorus, yes, sediment, but also some metals and E. coli. So that was kind of exciting. And we thought, well, let's put this in some other places. And since we don't have to worry about oxygen, maybe this is a good one to put in an underground situation. So this is an underground vault that has spent lime in it. You can see that chalky stuff on the bottom. And this is at the intersection of Frost and Kennard in Maplewood. And this takes runoff. This is a little more of a regional system. So it takes runoff from residential areas through some wetlands and some ponds. And in this application, we actually diverted high flows through this material instead of low flows, because we were learning from some other projects in some other parts of the metro that spent lime's Achilles heel is you don't want to load it with water constantly, or it starts to get gummy and kind of collapse and it won't filter anymore. So we put that knowledge to good use here and designed this to be a high flow bypass. So high flows come into this filter and then it gets a little time to dry out in between events. This one's also been doing pretty well. We're monitoring it. And then we thought, okay, now let's try some moving parts. Let's do a surface feature. Let's take water off of a wetland. So we're still doing kind of a more regional system, but let's pulse it. Let's bring the water in for our time, fill up the filter, then shut a gate so the water doesn't come in anymore, let it filter down, and then give it some time to dry out. So we got a little more sophisticated with the technology. And with this one, we've had some bugs with the tech. I mean, moving parts are great, but sometimes they're kind of a pain. You have to figure out how to get it to work. There's some things that go wrong in the field. This one's finally up and running. Actually, it was up and running last year, but then we got a drought, so we didn't get any water to monitor. So this is the first year that this one will be online and will be fully monitored. And then the last type of media I wanted to mention is CC17. The other thing we've been looking at is like, okay, what if we do want to load water in all the time? What media would be appropriate for that? And so we've been putting some installations in with CC17, which is a crushed limestone material. This is a project for South Washington Watershed District where water's coming in off of a wetland. That's a rendering photo. This is what it looks like built. So the CC17 material is in the middle here. So we'll be monitoring this and seeing how this goes as water comes in to this system this year. And with all of this, we're still testing media. We're still trying to identify what media is best for what site. And actually, the full evolution of this is a project that was recently put in for 9 Mile Creek Watershed District in the city of Edina. So this is the Roslyn Park stormwater filter. And this one is really built like a kind of a small treatment plant. So there's an aeration manhole that comes into some pretreatment cells. You can see the green arrows there. Those are pretreatment cells that have anthracite in them. Water comes down through the anthracite and then comes up through 3 different cells of different kinds of media that they're testing, and then out into a lake that's impaired. So much more sophisticated. You know, this is the vault system. They're testing different kinds of media. This is actually where it comes out into the parking lot and into the lake downstream. So when I look at that evolution, you know, you think back to, again, that Beam Avenue filter, that Minnesota filter, pretty simple, really. We've really evolved to look at filtration media that is able to accept regional runoff, so larger systems. And actually, we've built in more sophistication as we've gone, because we've found how these filters can be kind of finicky. Every site is very different. And so we like to try things like moving parts. We like to try gates. We like to try things that allow us to tweak these designs once they're in, as we learn from them, because we are continuing to learn from them. And sites like this allow us to really do that in great detail. So I'm sure I probably have about 2 minutes left, Andy. Okay, so here's the bottom line. I'm going to flash you through some bottom line takeaways here. So many things can affect a filter's performance. You have to really choose the right site, and that depends on what your treatment goals are and what site you're dealing with. Consider the chemistry of your site and the treatment goals in your design. Consider adjustable parts in your design so that you can learn as you go and make some small changes. Design for monitoring. Design for maintenance. Supervised construction. Things can go wrong during construction that can ultimately undermine your functionality. And then monitor and maintain. I think there's a lot of filters that go in that get put in and then walked away, and I can guarantee most of those are failing right now. So we have to be watching these sites. We have to be tweaking them and learning as we go, and then sharing what we've learned with the greater community. And I guess the last thing I'll say is that for these kinds of projects, partnerships are super critical. I shouldn't say that at SAFL. That means a very different thing. Super critical. Partnerships are critical for finding sites, trying new things, and learning from experiences for monitoring and maintenance. And so I just wanted to give a heartfelt thank you to the U of M SAFL, to cities, to watershed districts who allow practitioners like me to try these new things and to learn from them. They take on risk when they do that. And we can't move forward as a community of folks trying to improve water quality in the state of Minnesota without those partnerships. So thank you to all of you, and thanks for having me here today. It's great to be here.
Thank you, Erin. We have time for one question. We'll try online to see what we have there. Maybe we'll take a question from in-house.
They're still just warming up.
Yeah. Okay.
Oh, here.
I should have taken mine.
My question was about your vault system. It seems like you were setting up a system to look at different medias within there that you could change out. Was that a special design for that vault, or was it like a construct in place, or?
It was a special design designed specifically to be able to assess 3 different types of media.
All right. So there wasn't any prefabricated or anything like that.
You know, I don't know if it was it cast in place, Ross? Do you remember? Cast in place. Yeah. Yeah. We often do that. I mean, we're building another one right now in near Lake Emily. And yeah, we do end up doing a lot of cast in place. You don't have to do that, but
right.
We have specific things we want to do.
No,
So
I understand.
Yeah.
Trying to implement other.
Yeah. Yep. Okay.
Take one more question from online. Don't have one? Okay. All right. Thank you. And now we're going to hear from Mei Kai from the Natural Resources Research Institute.
Thank you. Hello, so I'm going to talk to reuse of solid waste as a filtration media, and particularly on the roadside application. So Erin already talked 2 types of media. They use ion enhanced sand or the spent lime. We will expand more material that could be used. So first thing that we always check that the media function, it could support the plant growth, it could filter water, it could be or remove chemicals or some things. But one important thing is that cost. So cost is always a very important factor to be considered during the actual application. So we wanted to look for any affordable or locally available material. Because of the cost, we will think, okay, can we use some waste material as a filtration media? So first thing we consider is that like the peat-rich material. You know, Minnesota is rich in peat. So we have a wide peatland. And even the second picture, that's a peat pile. That's what we call the savage peat. Actually, it comes from road construction. During the road construction, you dig the land, then the savage peat were piled there. And the last one is the peat screen. That's a byproduct from the peat industry. Second, also the drainage sediment. So any waterways, they usually collect the drainage sediment. They clean the waterway regularly, so you can get this material regularly. So the left picture from the Duluth Harbor and the right picture is from the Mississippi River. You can see from a visual check, they are different. The Duluth Harbor, the sediment is more like a regular soil, but the Mississippi one is more like a sand. So completely different. The other one also industrial waste. There are tons of industrial waste, and tailing definitely is one of them because of the mining industry here. So they have a lot of different size tailings, fine tailing, coarse tailings, and also like bottom ash. If you have a burners, it's always have bottom ash. And the lime mud, something comes from the process. And also some waste from the public works, like the street sweepings. Every spring, we collect so many street sweepings, also recycled concrete. So with this material, how can we check if they could be used or not used as the filtration media? That's something we are doing. First thing, we are doing lab testings. We always create an inventory for the material. We want to see how much this will be available. It is not a one-time material. We want it to be continuous available. And we also want to see if there are any existing data. After that, we evaluate them from 3 aspects, including like a biological, environmental, or civil engineering performance. So for the biological, we primarily focus on the plant growth testing. But something we never thought before is that invasive species, because it's a waste material, you don't know if there are any seeds of the invasive species are included there. So that's the recently we also increased that research area. And for the environmental area, we definitely want to see if it will release any contaminants, or if it could be remove any chemicals like metals or nutrients. And civil engineering, definitely in filtration performance, water retention capacity, all of those needed to be characterized. Besides the lab test, we also built several experiment plots in NRRI parking lot. So we digged that out and put the media we select there. Then we collect the water on the media, then to do the lab testing. This site was constructed in 2016. So we started monitoring from 2017 until now we are still doing. And next week, we are going to build another new 6 plots with other medias we select. So then from some simple findings from our lab testing or field testing, so materials that could be potential as the biofiltration media. This is not the full list. I just selected some of them. Like the savage peat or any peat byproduct, they are pretty good in remove metals or nutrients, and they are basically could be exchangeable with the compost. But we know compost release phosphor, but those savage pit does not. So pretty good. Drainage sediment, it's interesting that as the picture I showed, they have the different physical looking and also different textures for the material. So we noticed that like Duluth Harbor's drainage material, it does able to absorb metals. But for the Mississippi's ones, that like a sand kind, it does not have this function, but it's more exchangeable with the regular sand. And the taconite tailing, and taconite tailing could remove phosphor, especially if it's in the a little bit acidic condition, like a pH a little bit above 6, then that at that condition, it perform pretty good to remove phosphor. Because it uses a waste material, we do have a lot of issues. Some things, regulations, requirement. And we initially thought probably we can use a biosolid, but the biosolid we collect that is classified as Class B. So like Class B, they have the requirement that in the first year of application, that land is not allowed the public access. So if we want to use on the roadside, it's definitely not ideal for the biosolid. And invasive species, as I mentioned, we noticed that one from the drainage sediment. To be honest, we don't know where it comes from because the drainage sediment, it was parked outdoor for a couple of years already before we collect. So we're not sure if it collect from the material itself or if because it was in natural condition, some seed that added to the drainage sediment. And also material properties. That's the interesting thing. Some things they are pretty good on one side, but not good on the other side. It's difficult to get a perfect one. Like for the bottom ash, it's pretty good to remove metals, but it is a basic. So the pH is above 10. So you will think, okay, maybe I should mix with something to make it more neutral than to get the two functions. So there are very trick to get a recipe, the working recipe to do it. And the last one also emerging contaminants, because we are talking a lot of emerging contaminants. Then people heard, oh, waste material. Is there any emerging contaminants? Should we not use the waste material? If you say waste, the word waste, it's really hurt those people. So some people say, okay, don't call the drainage sediment as a waste. It's a kind of product. So there are many things. So we are doing the researching, and we started that from 2015, and we are keep working here. So interesting thing that to use the waste material save cost, but we needed to identify a good recipe for the application. So that's what I have. It's question time.
Thank you.
Okay.
So what sort of questions do you have for me? Any from online? Yes. Oh.
So what kind of emerging contaminants might you expect to find or be most concerned about on your materials, and what materials do you think they're the most likely to be present in?
So the question is that we first met is from MinDOT because it's a road application. They said, okay, is there any PFAS? And he really hated to use the industry waste material because he said, maybe there are PFAS inside. We should not use that one. So that's why we want to add those kind of tests in our lab characterization work. Yeah. Thank you.
Okay, thank you, May. And now we're going to hear from Erik Megow. Thanks.
All right, there we go here. Let's go. Oh, there we go. All right. I'm Erik Megow. Can you all hear me? I think, yeah. All right. I'm Erik Megow, Senior Water Resources Engineer with Stantec. My expertise for today is my work with using biochar as a filtration media amendment. And this was our focus for this was to remove bacteria. So this is a good complement to what Erin did. I was in a much similar situation. These being some of my first large design projects, putting my, PE on those. So this is building on the iron enhanced sand filters and then adding biochar. So the first two large scale filters we built, we didn't start with large scale filters. That'll be the next slide. But the first two large scale filters we designed and constructed in 2019 and 2020. The Woodcrest filter shown there, the yellow is the drainage. I know some people like maps. And we did a Pleasure Creek filter. The Pleasure Creek filter was a pumped filter. So we actually pumped it because we didn't have any head. And then the Woodcrest filter was your kind of pond retrofit, but it was a large pond retrofit. And those treated about 90%, or the Woodcrest was about 0.9 square miles of drainage area, and the Pleasure Creek was 0.6. So that's what they did. These were kind of larger scale regional filters. And both filters, we wanted to do iron enhanced sand filter against the biochar and iron enhanced sand filter. So at both of those filters, we did 2 cells, one with iron enhanced sand, one with biochar, and we split the drain tile, which was fun designing. So we're monitoring those, and we've been monitoring those since they went online in 2020. And I think we have data from 2022, and then we have some more going online this year. We have 3 more that we'll also be getting some monitoring data from. So those are the first 2. Summary from these filters in the first 3 years. The biochar amendments to the sand filters can have the ability to increase the E. coli removal up to 20%, especially when our influent concentrations were high for bacteria. We had some bacteria and dissolved phosphorus situations where we're actually leaching some of those contaminants during some storm events when we were monitoring them because they were just so low. We realized adding biochar to the iron enhanced sand filters did not significantly impact the phosphorus removal. So we were still getting, when we were monitoring these, we were monitoring for E. coli removal, or the bacteria, and total phosphorus and orthophosphorus. So we were monitoring for all those 3 things, and we didn't see a large reduction between the iron enhanced sand filter cell and the biochar filter cell. And we thought we might because we're reducing the amount of iron enhanced sand in that filter. But the biochar was a low cost, low risk media amendment. And we realized between the 2 different cells, we only had about a 6% increase. And we had biochar unit prices of installed about $330 to $273. So although the increase from the biochar to the iron enhanced sand is more than 6%, it was only installed at 25 to 30%. So that's where that 6% comes from. And then kind of next steps, lessons learned. I got 3 lessons learned here I'll go through, but the first next steps, we're kind of looking at biochar in different applications. One is to maybe look at removing or how they can reduce pesticides, heavy metals, PAHs, and Sarah Elliott and Richard Kiesling of USGS are going to go monitor some of those CECs, I think this summer, on some of our filters that we have installed. So the first lesson learned that we had was going from that laboratory to the field. And Bridget in her talk actually did a very good job, much better than I can do, of going through that process. I kind of stepped in after those pilot tests. So we did some pilot studies, catch basin inserts, in-stream job boxes, some small pond retrofits, some small pump filters, and then we went to these larger scale filters. But when we were going to those large scale filters, from the pilot test to the field, we realized we didn't have any local biochar being produced in the quantities we needed. So we found 4 biochars that could possibly get us the quantities we needed, up to 130 cubic yards. And then we sent those specimens to the UCLA Samueli lab, which is, or the Mahatni lab. Sanjay Mahatni helped us out, and we realized, all right, these are all still removing bacteria at levels that we needed. And we ended up going with that agricultural carbon one, but that was just, it's not linear. Sometimes you need to go back to the lab, especially when you're going from pilot studies to field applications. Then the next lesson learned was just installation. we're using a new media. How do we install it with the iron enhanced sand filter? The very first, I think, kind of mid-sized filter we did was up for a site. It was the city of Fridley. And for that one, it was a small filter for the Civic Center. And when we first installed this, we did a layer of sand, a layer of biochar, and a layer of sand. But after about a month, they called and said, hey, this thing isn't working. And we realized that biochar layer just created a cake, and it was just a hydraulic restriction. So after they tilled it up, it's been working for the last, I think, 3+ years. So that was just one thing we ran into. At this project, our supplier kind of dropped out. And so we still had to install the iron enhanced sand. And then you can see on the cell closest to us, there's a little berm down the middle of the cells that separates them. But at the cell closest to us, this is the Woodcrest filter. We're actually tilling in the biochar on top. Biochar has a specific gravity of 1 or right around there. And so we didn't see we weren't worried about it just washing away. So we actually just tilled this into the top 8 inches. I think moving forward, I think the best application is just to have it mixed off-site. You know, a lot of times you can get pre-mixed iron enhanced sand, but you can't get iron enhanced sand with biochar yet. But you know, Playsteds is a place that can do it. They have their proprietary mixing device, and then a couple contractors can do it off-site. But when we need to do it on-site, I think we would just do a layer of sand, layer of biochar, till them together, another layer of sand, another layer of biochar, till them together, and then just add another layer of sand. But that installation could be a little bit tricky with different contractors. But and then I guess the other lesson learned, number 3, was just maintaining hydraulic connectivity. So this is the same filter. This filter's been working good. It's been maintaining that hydraulic capacity, but you know, with our low number of available biochars. Yep. All right. Thanks. With our low number of biochars that we have available, we can't specify to them what gradation we need. So, you know, we can specify for our aggregate filter material sand what hydraulic conductivity we need using, you know, their gradation. But with biochar, we're just not there. We can't tell these manufacturers how to make it because we're such a small user of their biochar. And then the second part of that is, even when we install it, it needs to be maintained with the iron enhanced sand. It needs to be tilled. You need to break that top layer. And the biochar does break down. So even if you do get a biochar that fits your, you know, your gradient perfectly, you have the right uniformity coefficient that you're looking for, over time, it's going to break down. So you're still going to have fines. One thing we did do is go from a 30% addition to a 25% by volume addition of biochar to see how that might maintain that hydraulic capacity. But those are the 3 lessons learned. We have some ongoing projects. We have 3 more filters going online this year. We're working with a couple professors at the University of Minnesota exploring PFAS and micro remediation and biochar, maybe using biochar in septic systems. And then from that test that we did with the University of UCLA, that we did publish a paper with them looking at some of the how to, you know, produce your biochar to predict E. coli removal. So that's all I got, and I think I'm out of time. So
Okay, thank you. We have time for one question. Okay, we'll have.
So, so this question comes from Jeremy Fink. They ask, what is the target hydraulic capacity for these biochar systems? Is that meant to maintain a specific contact time?
no, the contact time, we realize if we have 15 to 18 inches, we have what we need. I think we design our filters long-term to pass like 2 to 3 inches per hour is what we design, especially for our pump-based filters. We make sure that we have our pump can operate between like 1 and 3. Some of these filters, when they first go online, they could be up at 10 or 11. So we're okay with them designing them for 3 to get that 48-hour drawdown. And it's also good for the biochar to dry out and iron enhanced sand to dry out in between storm events. So hope I answered that question.
Okay, thank you, Eric. Now we'll hear from Mike Isensee.
Right. Good afternoon, everyone. Andy asked me to share my experience with bioretention media. So I thought probably the best way to do this is just kind of walk back through the last 21 years of urban stormwater management, working for 4 organizations that's led us kind of this point right now. So this is really a perspective from a practitioner. So it really started in 2002 when we started promoting low impact development in the Twin Cities area, and we realized the number of pollutants and the scale of the issue that we were really trying to address in urban areas. And early on, when we started building bioretention basins in 2005, 2006 era, the Minnesota Stormwater Manual really recommended that our media be based on compost sand mixture. And so just to note that I'm going to say sand a lot. What I mean is C33 wash sand, which is something we learned right away in 2006 after an installation that it has to be washed. And when I say compost, I'm referring to leaf litter compost per the specs. So then we got to 2009, and I call that our soluble phosphorus awakening moment. And I think our big challenge for water resource management is that that component that soluble phosphorus is 5 times more bioavailable than total phosphorus. So it really can't be ignored. And then we got the news that our bioretention basins that had underdrains in them, now called biofiltration basins, were leaching compost from the underdrains. So we started addressing this through two different approaches. One, we've got a lot of soluble phosphorus that's naturally occurring on landscape. And so about that same time, St. Anthony's Falls Laboratory had developed the iron enhanced sand filter technology. And as Erin had pointed out, Barr had taken the lead in installing the first practice, and we were seeing positive results from that. So we started implementing iron enhanced sand as well as other practitioners around the state of Minnesota. So currently in the Carnelian Marine St. Croix Watershed District, we have 2 regional iron enhanced sand filters that have been in for 8 years and 5 years, and we are continuously monitoring those and really hoping for a good metadata analysis somewhere down the road, so if we get some better specifications on those. And I know that the U of M is working on that, which is great. So we started implementing that. At the same time, we started playing with different types of medias. What we were looking for is material that could be mixed with sand. We were trying to keep the mixes simple because doing complex mixes for small scale projects is cost prohibitive as well. It greatly opens up the palette of errors that can occur on a project that results in failure. So we worked with Coir pith for a while. If you're not familiar with that, it's like sawdust. Except it comes from Coir. It would work great. It doesn't release phosphorus. It creates a great structure, organic structure in the soil to grow microbial communities, and we had great plant growth on it. Unfortunately, we're shipping it up from Florida, and it was about twice as expensive as our other media additives. So we quickly abandoned that. And so then we tried slimming down our compost mixtures from 30% to 20%, and that still was producing high phosphorus outputs. We were doing a lot of soil testing back then. These are some of the results from the tests that we were doing from 2013 to 2015. And you can see that the compost mixtures, even at 20%, we're not meeting the Stormwater Manual standard of 12 to 30 milligrams per kilogram of phosphorus. That came from North Carolina State University when they were doing the Stormwater Manual update as a good indicator whether or not your filtration material would be losing excessive phosphorus. So all of our peat samples that we were getting, however, were coming in within that standard. And so that's really what we went with, we're going with for a lot of our designs. Concurrent with that, in 2016, the Minnesota Stormwater Research Council finally got off the ground with some funding, and really the goal of that entity, which has been functioning and producing a lot of great data for practitioners since 2016, was really to do that facilitation of the completion of applied research. which is really what we're talking about today, is how do we get this information that we need to do better designs and allow practitioners to meet their objectives for water resource management. So when that came out, I actually contacted Andy and Erin, who's in the room with us today, Mike Trojan, who I'm sure is online, even though he's officially retired now, as well as a number of others. And we set out to put a proposal together to what ended up by being a set of large mesocosms on site here. And I know that everyone here is familiar with the work that St. Anthony's Falls Laboratory has been doing with that, and that's been great. But while that was going on, we were still designing and building. And so I just thought I would run out. I took a field tour yesterday of some of the past projects going on during this phase. Up in the left, that's a large bioretention basin in Stillwater. It's got a 2-foot profile of 80% sand, 20% peat. So our basins, that was seeded and plugged. And then I just want to point out too that so maybe my primary point is that the sand peat mixture is working really well for growing vegetation and meeting our phosphorus reduction goals. The upper right hand slide though kind of demonstrates that we're getting more creative with how we use our media. So this is a foot of 70% sand, 30% peat, a foot of 100% sand in the lower portion, and then an iron enhanced sand filter. And what does that look like in design? Because it's kind of hard to see it in the field. So really we have the base media as the ASTM C33 coarse wash sand, and as primarily because in bioretention design, you want to get that internal water storage. There's a lot of biological processing that occurs there, and it gives your stormwater runoff the opportunity to infiltrate even in poorly draining soils, which is typically where we're at when we're using filtration media or filtration design. And then the majority of the basin is biofiltration media, and so that's a peat mixture with sand. But the under drains are actually located in sections of the cell that have bioretention media. And then the one part that I would note with this design is notice that the impermeable barrier separating the iron enhanced sand filter media and the top media, there's a space up there, and that's because we really want a foot of aerobic activity in our soils to continue to get the benefits for that processing, microbial processing in the upper portions of the soil. The other approach that we've taken fairly often is the upper right, where we have the bioretention media at the inflow point of the basin, and at the very back of the basin, we do another cell of iron enhanced sand filter with the underdrain. So the stormwater, our first goal is to capture, infiltrate, filtrate as much as we can. But before the water hits that underdrain and heads out, we have a iron enhanced sand filter media media that it passes through. But I also want to note on this design that one of the challenges with designing these systems with the underdrains is that they tend to be bypass is a high probability. So you want to design it thinking about where's the water going to flow and maximizing the flow path, both through the bioretention media, but especially through the iron enhanced sand filter media before it can get to the underdrain. Because it will drop right into the underdrain and it will basically utilize all the capacity in a small area if your design doesn't consider that. So where is the research now? Some really cool things that came out of the work that the University of Minnesota is doing is and MPCA's pushing for reusing waste products as food residue compost. I think there were some really good findings coming out of the mesocosms, and we look forward to using those in the future in our infiltration basins. Spent lime, as we've talked about, biochar that we've talked about, as May talked about, taconite tailings. But we're really where this is going is I think this was best put in a proposal by MnDOT to the local road research board, is we really need continued research on these high volume byproducts and waste materials from all of these different industries, because at the end of the day, our material has to be local and sustainable. So it's good that we have some options that we can work with now, but I'm looking forward to that improving. But in the meantime, our basic standard right now is 80-20 sand peat mix with an elevated underdrains and gate valves on our smaller scale practices. And then larger scale practices like commercial, industrial, regional, then we're incorporating iron enhanced sand if in most of those cases where we don't have where we need to move to filtration. So that's all I've got. Thank you so much.
Thank you, Mike. So we have time for one or two questions, one from online.
Hi. Are the mixed percentages by weight or by volume? And is there a specific threshold of OM content where P leaching begins?
Yeah, great question. So for the organics mixes, those are by volume. For the iron enhanced sand, that's by weight. Yeah, there's a lot of literature out there about percent organic material in soil. 5 to 8% will grow vegetation. A lot of our, I think a lot of our mixes are probably in the upper thresholds of like 10 to 12. But there's not a specific target really. If you look in the Minnesota Stormwater Manual right now, the primary things that you're looking for is you're looking for yeah, right. Actually, organic content is in there. Your soluble phosphorus and then your soluble salts. So you don't want your salts to be too high either. And that was one of the concerns we had initially when we were using coir pith. But the industry down in Florida does a great job of testing that material. So we didn't measure any high salts in that content. So yeah.
One more question from in-house. Erik?
You said your current biofiltration media is 80-20. Pete, have you tried using any iron enhanced sand or iron filings with that mixture?
Yeah, great question. So that's we actually talked about that when we were doing the mesocosms as well. And until we have testing data that shows that you can mix the iron in with the organics, we prefer to keep them separated. The other issue is that we know that iron tends to inhibit vegetative growth. So I think we're already pushing the envelope with such a thin mix as far as nutrients have the peat in. And so I've always been concerned about throwing in, which would be another vegetation stressor on top of that.
Okay, thank you, Michael. So we'll take a quick break, but I'd like to say the people online and the people in-house need to come up with questions because we'll come back and we'll have a panel answer questions. So I don't see many questions coming from in-house. But you can see that we're just starting on this whole problem of media, which is amazing considering that we have been producing biofilters for 30 years. 30 years later, we're just starting on figuring out what we are doing to the water that flows through it. And that's phenomenal to me. So there's a lot of work to do, a lot of questions to ask. So please come back. We'll be back in 5 minutes and start with the panel question and answer period. Thank you. Okay, we are back. This is a Minnesota Stormwater Seminars panel on stormwater media. You heard from each of the 4 new panelists on the perspective they bring to the discussion. Questions have been accumulating, hopefully. Online participants have been voting, hopefully, on those they want most answered by the panel. So let's start with one from online.
Okay, so this question we've been saving for a little bit because we wanted to make sure everyone had a chance to share their information first. This question's from Joe Fox. They ask, should we be using what we're learning in these last few seminars right away, or should we wait until the Minnesota Stormwater Manual is updated to reflect the research and information prescribed?
There's no one from MPCA here.
Go ahead.
I guess I mean, barring any, legal / permitting questions, which of course wants to be by the book for that. But I mean, I've seen many times if you have an entity that's willing to take the forefront and implement something and monitor it and learn from it, sometimes that informs the stormwater manual. So I think it's important for people to take calculated, careful risks to try new things, because that's how we move forward. We can't wait for it to be perfectly figured out and in a manual before we're implementing. I don't know that anything that's in the stormwater manual, you know, I think there's things that are in there because of things people have tried and learned from. So I would say it's great when we can put things in the ground and learn from them and then inform back to the community, and it's a cycle that keeps going. So I'd say don't wait if you don't have to.
Yeah, to piggyback on that, sorry. All right. You hear me? Am I good up there? All right. To piggyback on that, take small risks with it and try to monitor it. If you can monitor it, that's great. Then you know if it's working or whatever. If you just install it and say, okay, well, it's still drawn down in 48 hours, I'm fine, you know. But if you could start out small, we started out really small with our biochar stuff. We were looking at insert catch basins, and we were looking at it was a small buildup when we were adding biochar to these because we didn't have a whole lot of data for it. You know, we had some data from the laboratory and whatnot, but yeah, so the small risks, and you'll learn some lessons in those. And we even learned some lessons when we thought we were all systems go on some of our large regional designs.
So, and I would just add, if you're not in college, I encourage you to plagiarize. There are a lot of good plans out there, and there are a lot of folks who have been implementing these practices. So definitely reach out there's a lot of resources. If you're not sure if somebody's done something, you could go right to the Minnesota Stormwater Research Council, and all of our contact information is on there. We've seen a lot of great proposals and projects come through, and as part of kind of our small stormwater community, and we can connect you to some folks, like if you're going to be using biochar, iron enhanced sand, or if you're just simply looking for some design cross sections for how to implement iron enhanced sand in combination with bioretention. It's all out there.
And if you're going to be using a new material, I strongly recommend using something that's already been tested in the lab, and not just, oh, biochar has been tested in the lab, the specific biochar, the specific material, and even May showed how not all sediment is sediment, and it can vary widely. And if you don't have access to that data, trying to do some type of small batch test just to see if you see removal of your target contaminant with your actual water. And you know, it may be a little bit more budget up front to do some of the analytical work, but it could save you a lot of trouble in the future just doing some simple tests.
Mm-hmm.
Yeah, I completely agree with all others, and also don't worry about that. Oh, you don't have money to do that kind of pre-test. Maybe we have small funding could help you also. So just contact us to get more information, to get more background, then do it. And even for monitoring, probably we could help you. And the other thing is that even at the end, it's failed, but it is a lesson learned still. So really just do it. You cannot wait. Then contact us, prepare us, then make a good design, then do a small scale, then get the more experience, then expand. That's basically a process.
Okay, thank you. Do we have a question from in-house for the panel? Yes.
What does the target, longevity or lifespan of these different kinds of filtration ponds look like? And once the media is expended, what's the ultimate fate of the materials?
That's a good question. Who wants to take that?
Maybe I'll start. Oftentimes these things are tested in the lab, kind of to build on some of the answers that have already been given. We often start these things testing in the lab, and we get a sense of their longevity, their capacity, and what they can do. But it's not until we implement them in the field that we really understand how long they can last in the real world. So we often see differences between lab and field, or even lab and pilot. So until we do some of that, we really don't know. And even in that case, we learn things along the way that we didn't anticipate or couldn't measure in the laboratory. So we have some data on some of these new things. We have good data on some of the older designs, but we're always learning.
And we're in the process of determining the life of many of these practices.
Yeah, no, and when we first started,
Yeah, you can keep it on.
When we first started thinking of adding biochar to the iron enhanced sand, we were kind of, I think, Andy, you had a calculator at the time that kind of looked at, all right, how quickly would we use up these iron? And I think at the time with how much we were using at 5% or 7%, I don't remember what we were using at that time. It was about 10 years for like an 18-inch media section at 5 to 7%. And yeah, it's also based on what your incoming loads are. If you have higher DO loads, or not DO, dissolved phosphorus loads coming in, the iron will get used up faster. Just for the biochar, we don't know how long that's going to go. That's a different process than the iron enhanced sand, which I'm sure you could explain a lot better, but it's more absorption. And, you know, what it's doing is just grabbing that bacteria and then holding it there. And then when it dries out, that bacteria dies off. So we don't know as far as when we would need to change it out. It could just be as simple as tilling in more iron filings or tilling in more tilling in more biochar, but then you're also running the risk of, you know, reducing your hydraulic capacity. So it's a little bit of a game. And as Erin said before, every site is unique. So.
And it also depends, as you said, on the process and the contaminant. And if that contaminant is going to degrade in situ, or if it's just going to become a sink. So for example, with pesticides, you might expect that these compounds degrade in soil. They might also be degrading in your treatment system. But when you're thinking about PFAS, and if that's a concern, those contaminants don't degrade under environmental conditions. So you actually are just creating a sink of your pollutant. So in that case, the consideration of when the material actually needs to be removed is critical, and can be predicted based on lab tests, but it's almost impossible to really simulate the complexity of what's going on the ground. So it still needs to be combined with monitoring. And then don't give me, yeah. That's still a big question.
And I think actually, if I can build on that, you know, any of these media can potentially remove multiple things. So even if you're targeting phosphorus or targeting metals or something else, there could be something else on there. So thinking about what this media ultimately is at the end of its life, characterizing that before we really can understand what to do with it is important.
Yeah. Yeah. So we don't know, you know, if biochar can remove any of these other, you know, medias. I think Bridget's done some, but the ones we have installed, that's why USGS is actually interested in some of our filters right now to actually monitor those. The only contaminants we're monitoring on those are phosphorus and bacteria right now. So could it have better benefits for some of these other CECs? You know, that it just needs to be monitored, but sometimes the monitor and testing can be very expensive. I think PFAS testing is very expensive through some of the labs here. So
I think your question is especially relevant because I think we've spent a lot of time implementing these projects over the last 10, 20 years. I don't think we've really seen a lot of these filters come to a lot like an obvious end where it's like, and now we rebuild it. Like that's probably the next decade. Really, I mean, honestly, I mean, I don't know of many filters that have been built that have been like, oh, now this one is full. We're going to start over. We've been implementing them and monitoring them. There are filters that fail for different reasons and those get rebuilt. But in terms of one filling up with phosphorus, I don't think we've necessarily started to see these things come back to roost. And that will happen. We set those expectations with clients when they go in, but that's something we're watching for and we'll see.
Okay. Do we have a question from online? Okay.
Thank you. Okay, we do have a question from online. This is from John. They ask, I've heard that peat is apparently a scarce resource. If true, are there alternatives?
We missed the first part of that question.
Yes, I'm sorry. John asks, I've heard that peat is apparently a scarce resource. If true, are there alternatives to peat?
Peat comes from the land after a long time. We are using them. That's called savage peat, and it's difficult because we are using their continuous producing now at the same time. Depending consumption, if it's faster than the production, it could be, but at recent years, we cannot see that it will be used up soon. So it's difficult to say now. Yeah.
Yeah, I'll maybe add on to that. So, right, peat is what is working right now. And that's why I think that where the research is going is good, because it's, I think the peat industry argues that it is a renewable resource, the time for renewal is a lot longer than projected time for consumption. And so it is not the silver bullet yet for bioretention media. It meets a number of the parameters that we need right now to protect and restore water resources. But for the long term, we definitely need an alternative that maybe hopefully comes from our waste cycle that we've got a lot of and would be local and would not have any additional contaminants or issues when we add it to the media.
Unicorn media.
Anyone else on peat? Okay, we have a question here from Ross Bittner.
I want you to speculate a little bit about, what's the media that's most valuable out there? And then how do you think about value? So I'll give you an example. When we're just thinking about phosphorus, we often will think about dollars per pound of phosphorus life cycle. But when your filters can start to remove so many different contaminants, can you start to think about a decision matrix where you're, dollars per log removal of bacteria, dollars per pound of nitrogen, dollars per pound of sediment, when they can do multiple things, how do you start to judge that? Who's done that type of work? And then what's your best bet right now? If you were to put some chips down on a certain media type that can do all of those things, what should we be using, or what should we be studying to know for sure?
So one way we currently using the life cycle assessment that is included in our project also. Yeah, there is life cycle assessment including the cost evaluation, also the environment impact. For the environment impact, they primarily to link the greenhouse air. So using that as an indicator to even you have multiple pollutant, then they using the greenhouse data, greenhouse air gas data as a number to get a value value. So this is a current way we are using now. Yeah, I'm not sure if you others have questions. Yeah.
I mean, I'm not going to say biochar is a silver bullet, but I'm an advocate. And one additional benefit that we haven't really talked about today that I think is going to be even more important in the future is the carbon sequestration benefits. So right now, at least I'm not aware of any, strong carbon offset markets, but I believe that's going to become very important in the future. And you can actually use the carbon that's sequestered in biochar when biochar is produced to, receive some of those credits. So that's, in addition to removing multiple contaminants, if you're considering that in a life cycle assessment, you can actually consider it a carbon negative aspect and offset your greenhouse gas emissions from other aspects of the project. So I'm not going to put my chips on it removing every contaminant all the time, but it does have some additional benefits, even if it's not removing your particular contaminant of interest. So.
So I think something to consider, many of the life cycle assessments and cost benefit analyses tools will consider the cost of the material in addition to what it removes. That comes into the cost benefit. But then also I think what's important is to the question earlier, like, what do we have to do with this material when it's done? Is there an additional cost to remove it, dispose of it? And also in between those two periods, between installation and between disposal and complete replacement, what are the maintenance costs? And so some of these media might require more or less maintenance than others. More or others might require more or less, and maybe maintenance specifically for vegetation, if these are vegetated systems, or other co-benefits for these practices. We try to ask a lot of our stormwater treatment practices. We try to ask them to do a lot of things. So there can be a lot of costs involved. And I feel like you have to break all of those pieces down to accurately get a dollar amount before you can think about then what are the benefits and how do you provide either a cost or some other metric on the benefits you get for it. But I think we only have some tools that are kind of getting halfway to what you're looking for, Ross.
Yeah, Ross, that's a good question. I think to piggyback on that, when we put those two biochar iron hand sand filters in, we got clean water fund grants. So they had us calculate out, or what's the 30-year maintenance. So we've been using that 30-year maintenance on a lot of our design of like, okay, bringing that back into an annualized, what is your contaminant of concern? Many times for the Clean Water Fund, it was phosphorus. So that's what we did for that. I mean, we added the biochar because in the two watersheds we were working with, Shingle Creek and Coon Creek, that's where we had bacteria impairments on those streams. So that's why they were looking at that. But if I had to pick one, thing right now, if you were looking at removing phosphorus, which a lot of times is as a permit reviewer or, as a city, I would push people to use, iron enhanced sand without, a vegetated layer, just because you can maintain it and whatnot. It's when you add that vegetated layer that iron enhanced sand becomes very difficult to maintain. You could have chunking. You don't know how that's going to mix with your organics and whatnot, as I think Mike was talking about too. So that's the best case. But a lot of times when these project applications or, people are doing these redevelopments and they're thinking about using iron enhanced sand, they also want the vegetated media on top. And that's where it's sometimes we have to permit it because the PCA manual does have some layering techniques and stuff that they can use, or some cities will do the, iron enhanced sand, right around the drain tile. So it hits that. And so I think there's some ideas out there, but I think if I just had to put in a project right now in targeted phosphorus, which is a lot of people's concern as far as the permitting goes, it would just be iron enhanced sand, unless you also had a bacteria impairment. Then you could use biochar, because I don't think that reduces that phosphorus. And then hopefully we'll learn from the USGS studies and more Bridget's work, what other contaminants that might be pulling out in the future. But we're just not monitoring for them right now.
Yeah, I like that response, but also I have to say the longer I'm in this biz, the more I'm also learning that we can't forget about reducing impervious surface, reducing erosion, and restoring urban soils. So that might be the best thing. I mean, Darren, I know we're a filtration unit and we love it. And we will. If you hire Erik and I, we will love to go crazy on your site. But it's true. I mean, we can build filters that are great. We can build them to be for a variety of pollutants, but ultimately the best thing we can do is probably reducing impervious surface where we started the problem in the first place. So just a plug for that. Let's not forget that.
Here's a question from Midhouse.
There was a lot of mention of peat today. I didn't hear compost. So are we ready to replace compost with peat? Do you
I was sitting here thinking about that. So I want to be clear that we're really talking about peat in the application of biofiltration. Most of our applications in my area are bioinfiltration. So
We are still using compost where we can. The challenge is when we put the under drain in the system. I think that for a small scale systems, which is the majority of what we're working with, a peat is probably going to be used for a while until we can find a suitable replacement that's local and hopefully more sustainable. But then for larger scale applications, the work with the mesocosms that show that we can actually treat some of the soluble phosphorus with iron enhanced sand in combination basins. So if we're talking industrial or regional, more regional basins for residential development, then I would say that that's probably a better long-term approach. And I would just note that I'm not a fan of the layered cake approach, which is where the research has been, just because if once the capacity of the iron is used, then you have to excavate the whole basin. So that's really the driver for our kind of 2 different media in a single cell, or maybe even in the future, 3 different media in a single cell, is to get all the functional values of the media in your one practice.
Yeah, actually that in the picture I showed, we have the savage peat from the road construction. Excuse me. They put back to the road, and because this is from this side is close, the cost is most important. When they put back, they also add 10% of compost. That does not mean we are not using any compost. We still wanted to mix. So that's something I mentioned is trick to develop a recipe, which one to mix to which one at what ratio. That's a lot of knowledge. And that side that is on the road. And we also monitored the water quality from 2018 that use 10% of savage peat, 10% of compost plus sand. That one we did not see the phosphor release. It's pretty low. It's pretty low concentration. So that's a good place. I think a lot of application of compost or peat is really depending on cost. How close, how is that available just nearby, or some transportation or the material cost. So compost could be used, but you need to see control the percentage. And we had the experiment plots. We use a 50% compost. We did see a lot of phosphor released. But after 5 years, the concentration decreased a lot, actually. The phosphor release decreased a lot. So it's really depending on your size. So, and the cost also.
And I just want to give a word of caution about compost. We look at the phosphate leaching from compost, but depending on what your compost is produced from, it can also contain PFAS. So those compostable containers you get that are marketed as green, they have to have something on them so the grease doesn't leach through them, and oftentimes it's PFAS. So these food-based composts can become a source of PFAS pollution. So I would just be critical of where you're getting your compost to make sure you're not replacing one pollutant for another. So
where you're getting your food.
Yeah,
McDonald's.
exactly.
No.
If I can add a couple things on compost, I think that's very important is the sources, where these composts come from, what the source material, the feedstock is, really determines how the compost turns out. I think that's true for biochar. It's true for many of these things. So always think about that, what is in there, and they all behave a little bit differently. So try to understand what it is you're using, and then try to find the best use for it. As Mike said, if we use these systems to support the vegetation, the microbial growth in the soil, removing metals, they can actually support bacteria that break down PAHs. So there's a lot of good things in the right spaces for compost use. I will mention I'm actually in the middle of a research project where we're doing an extensive lit review on the use of compost in stormwater applications. So if I go back actually to tag on to Ross's question, where would I put my chips? And use Erin's answer a little bit is we need to think more holistically and maybe treatment train. There are important tools for different parts of what we're trying to do. And compost is one tool in our toolbox. If used appropriately, it's fantastic to do what it's supposed to do. It can't be used for everything, just like anything. If I go back to Erin's first slide, there is no silver single bullet. We have to think about these things and find the right spaces to use them. So I'll add that about compost as well. So stay tuned for results on that extensive lit review on what we find.
Did that answer your question?
Okay, question from online.
Okay, perfect. This person asks, biochar comes in many different flavors with differing characteristics. Are there standards that will describe the most appropriate characteristic for the media?
But do you want me to expand on there's really a need for that, and the reason that we're lacking is really what Erik sort of explained in his talk, is that once you need to start working with biochar at a certain scale, there's only a few biochars that are available to you, and the stormwater market is not, it's like a tiny little component of the actual biochar market, which is mostly focused on soil amendments, and there are very different properties that you need to facilitate contaminant removal that are a bit more specific than just putting carbon in the ground in your soil to help grow your plants. So, I'm not gonna I'm not gonna speculate on this fully, but I will say that that's something that we're working on, is trying to fill that gap by producing some more sort of standard reference materials so we can specify certain properties that producers can potentially target to manufacture a product that can be used for specific stormwater applications. We're not there yet, but I think the momentum is moving in that direction. So
I can kind of piggyback on that. When it comes to biochar and bacteria, we knew from Sanjay Mahatny's first work that if we had a wood-based, a hardwood-based biochar, so that would be the feedstock of the biochar, and if we had temperatures, like kiln temperatures above 550 degrees Celsius, that's where we were getting, it was higher, that's where we were getting good bacteria removal. I'm sure you've done more work on that since, but
and I can piggyback on
yeah, so when we were looking for a larger, quantity volume, we found 4 manufacturers where their feedstock was wood and they had temperatures above 550 degrees. And then those 4 is what we sent, 5-gallon pails out to Sanjay to test again. And from those 4, manufacturers, I think one was Oregon, one was 2 were Michigan, and one was Missouri. From those commercial manufacturers, they all worked. They were all removing in the lab about 96% plus, but that was all the information we had, and then we kind of confirmed it on the back end. But as far as like getting a MnDOT, I think is right now working, Dwayne Stenland and his group is actually working on a biochar specification. I don't know if that's for soil amendment or stormwater phosphorus removal, but
roadside.
for roadside.
Yeah.
Okay.
Yeah.
And then I know Jim Doughton with the Minneapolis Health Group is getting a biochar facility online in the next couple of years, and that's kind of been. And I think the city of Lincoln, Nebraska also got a Bloomberg grant, and we were helping them design a facility. So there are some. Hopefully, we'll get some more local manufacturers where we can kind of dial in what we need.
Mm-hmm. And I'm violating the thing. I'm piggybacking off of your piggyback on mine. No, thank you. But I just there's a lot of recommendations of the feedstock and the production temperature, and those are usually the 2 main specifications. I just want to have the word of caution of relying too much on those, because there's a huge variability in the types of processing that can affect the final properties of the biochar, in addition to its temperature. So, for example, you don't know if it's pyrolyzed long enough to become fully charred. You don't know what type of quality control that the various producers have to hold at a certain temperature for a certain time. There's batch versus continuous processes. So that's a starting point, is the feedstock and the temperature. But what we really need is to find a way to confirm with simple tests that the product that you're getting in the end actually has the properties that you need. So and then everybody thinks surface area is that property, but there's actually a huge variability in the surface area quantification depending on what process is used and what technique is used. So right now it's, try to use something that's been tested in the lab, but we're hoping that in the future we can have more of those specifications. So
Okay, great.
For you.
Hey, I have a specific and then more of a general kind of, but related. So in the biochar, you noted that there's like issues with maintaining the desirable permeability. Have you experimented with increasing your coarse grain aggregate in your sand mix design at all?
I think you were directing that at me. I'm sorry.
Well, yeah.
No, we haven't yet. We're still using kind of our base, that the granular filter, and that's mainly what we have available to us as far as MnDOT, and that specificity on that grain, that uniform coefficient is what we can get, from Plasteads or some of the other manufacturers around here. It's so when you start playing with that, you specialize your, product, and then prices go up when you need to, specify that any further, I guess.
Yeah. So I guess the more general question, so is that so I don't do this kind of filter design, but I design dam filters. And C33 is a great filter, but it has a lot of gradation requirements for the use of like concrete mixes, and there are like looser aggregate or aggregates with looser requirements. So in general, like, have there been any use of not using C33 and for cheaper aggregate?
I think when you go to a larger aggregate, or with something with higher permeability, you might lose contact time. So I don't know. We haven't done any tests outside of that, but I think that's why people haven't looked at other things.
I think, well, I can't speak to a lot of the details behind this. I haven't personally been involved in these designs, but I know there are folks at Barr looking at granite sand and having that mixed with other materials that will bind phosphorus. At the rosin filter, that is the aggregate that's used to mix with a number of different things.
Can we use that other mic either?
I was just speaking to granite sand, which is something we've started to tinker with a bit, and using that combined with some other materials that will bind phosphorus. Granite sand is the aggregate that's used in that rosin filter. I keep pointing at Ross because it's in Edina. So that's one thing we've started to look at. It has a higher hydraulic conductivity. But otherwise we do use a lot of C33 sand as well. So.
I'll just say we haven't seen a lot of studies that are comparing different types of sand for filtration, and there are multiple, again, purposes. We want to filter particles, so TSS removal would be a kind of a key metric to measure. Permeability obviously would be a key metric to measure, but that certainly could be something that we could do. We could dive into some of these different sand distributions that are available and see what the relative comparison is for cost and performance for multiple metrics. So we certainly could do that.
Okay, further questions for the panel? One from online.
Hello. How much of a concern is the climate of the upper Midwest with these systems needing bacterial processes to work? Would these systems be better placed in southern climates?
Just a question. You can take that.
So my information just comes from preliminary reading of research that's out there. Yeah, we know that bioretention basins are moving water through the winter and spring. I guess I have not seen a lot of data out there on, like, for example, bioretention media. If we're getting a lot of microbial action and removal, what the inflow outflow is coming in and out of the winter season. But I can tell you anecdotally that we are delisting water bodies because of retrofitting these practices in our watersheds. And we're seeing improving long-term trends on water bodies that have historically had a lot of water quality issues. So my sense is that's definitely a black box regarding their function in the winter. But the real proof is in the pudding for me that we're achieving our goals with water resources. And we'll eventually get to untangling or understanding that black box of what's actually happening during the winter. But in the meantime, they're functioning. Maybe not as well as it would if we were in Florida, arguably, which maybe we should all go down and try.
I mean, they might work better, but we're here, so.
Okay. Other questions? We have one more from online.
Hello again. Is there a laboratory test to estimate phosphorus absorption holding capacity that can provide a reliable estimate of biofiltration system lifespan in this field?
Is there a laboratory test? We've used a number of different tests. For the most part, our best so far is actually to do a batch test, do a jar test. Many people have done those. They work very well to give you a sense of capacity. They're very scientifically proven and sound. We haven't found any way to kind of shortcut that process with a simple test. If I add on, this wasn't part of the question asked, but we also looked at a number of methods to measure compost, phosphate release, and other materials that might release phosphate or other contaminants. And similar, we haven't found any shortcuts or any easy ways to get that. So it's really, at least from what we've seen so far, batch tests, jar tests are the best state of the science so far.
But with phosphate and iron, there's a bit of a complicating factor with these batch tests because the material you buy from, I mean, you can buy it wherever. I'm not going to advocate for a particular place, but it contains reduced iron filings, and their mechanism of removing phosphate is actually adsorption to the oxidized phase that is created during in situ weathering. So, I guess it could be possible if you were to weather the material first before the jar tests, but I guess I was the one who advocated for simple jar tests, and now I'm criticizing the jar tests that Andy just suggested after I suggested that he answer the question first. But I think it's just, again, it comes down to what knowledge do you have of the material and what's the mechanism by which it's removing the contaminants, and if your experiment that you set up is simulating those. So.
Yeah, exactly, because the jar test, you only have water and the material. You don't have plants, bacteria, or many things. That's difficult to create the condition in a simple jar. So that's why we like to start a jar test. But once we know something, then we will go to the like a small plot testing, like a bucket or even greenhouse test. You have some plants there, you add bacteria, then we get more data, then expand. That's the way. So it's difficult to get just to use a jar test, then expand immediately to a large site application. Yeah, just a step by step. It cannot escape. Yeah.
One thing as far as the biochar characteristics go, when we were testing those, we did see with the physical characteristics of the biochar, some positive and negative correlations. One Bridget mentioned was the surface area. Biochar has a very complex surface area, and the higher the surface area, we were seeing better absorption of biochar. And then the other one was carbon content within the biochar. So those two were positively, they showed positive trends. So the higher carbon concentration and the higher surface area. The two negative ones were ash content. If you had lower ash content and if you had lower volatile matter within your biochar, then that showed that, the higher concentrations would kind of block those receptions along the biochar and you'd get less. So there was some positive and negative correlations, but we haven't dialed those. We can't specify right now. All right, biochar with less than 5% ash content, less than 10%, because it could just be a batch by batch, or, we just don't have the feedstock, capabilities of dialing that in just yet.
Okay, thank you very much. We have one final question for the panelists. And I'll start with May right here. What key takeaways would you give our audience for the conversation that you've had today?
So filtration media, I think they are very important, and spend some time to get more data before you use it. And there is just like Erin mentioned, there is no silver bulletin. So based on your problem, to select the one that will be best work for your situation.
Thank you. Erik?
Yeah, I think it's just getting as much data as you can before you go into like full field application. I mean, we do have to take some risks with this stuff because what we're doing in the lab isn't exactly what we're seeing out there. And finding good client partnership. I know Erin mentioned it before. She had some really good partners with some watersheds. We did too with Shingle Creek and Coon Creek, and they're continuing to be good partners, taking these, measured risks with us and like moving that, going from the lab to the field. It doesn't have to be one jump, doing some of those pilots so you reduce some of your risks, or you don't want to spend $500,000 on a filter that doesn't work. So
yeah, Bridget.
You two took two good ones, so maybe I'll continue. I think I'm going to go with the last point that I made then, after you both talked about getting data and testing at intermediate scales. Having a fundamental understanding of the processes, the actual chemical and biological processes that you're trying to facilitate in these systems, so you can critically understand, the unique circumstances or aspects of the design that need to be considered for success. So since there is no silver bullet, you can't replace just a fundamental understanding of the chemistry that is going on behind that. And I know some civil engineers might cringe at that idea, but it's very important just to understand the fundamental processes that are happening so you can make good decisions.
Yeah, I'll build on that. It's exactly where I was going to. But first, I should say that more research is needed. I don't know if there's anybody here that agrees. So we and I hope that we're able to continue the great work that's been done since 2016 in coordination with the Minnesota Stormwater Research Council. But most importantly, I think it's important to continue to innovate, but innovate within the parameters of the data. Look at the data, understand what it means, and then use that as the stepping stone for your innovation and design for your site constraints and opportunities, and your goals for, I'm going to just say water resources, because that's really why we're here, lakes, rivers, and streams. And with that thoughtful design process, we can achieve really good things for the folks in Minnesota.
Okay. They aren't leaving much for us, Andy. I will say, don't use Chat GPT to write your technical specs because things are happening in real time. We're learning project by project. It's not stuff you're going to find out there on the internet all the time. And also we did that for fun. We tried to write a technical, we did not use this technical spec, but we decided we'd see what Chat GPT came up with for iron enhanced sand. And it'll give you like the bare bones of something, but the true art of implementing these things is really a lot about details and a lot about knowledge that we're learning day to day and from people in this room. So ask questions, reach out, and like these folks have said, every site is a little bit different. And so you have to kind of start over every site. And yes, chemistry, super important. There you go.
Wow. I guess what I'll say in my key takeaways is, first, I actually greatly appreciate something about the Minnesota stormwater industry. And it's represented here with the folks at the table, the folks in the room, the folks online, is their willingness to take these measured risks, to look at data, look at lab data, look at research, and say, I want to try this before it's in the stormwater manual, before it's anywhere else. Their willingness to take these measured risks and try to push our industry forward into better and more effective treatment practices. And to add to that, don't be afraid to share your failures and lessons learned. Some of the talks we saw today were showing lessons learned. We can learn from failures. We can learn from successes. We arguably might learn more from failures. And if we hide those, then somebody else is going to make that same mistake. So don't be afraid to help everybody learn and advance the science and the industry and what we know and what we can do and how we can improve our protection of water resources. I'll leave it at that. Thank you.
So that closes the panel discussion, but we have one more thing on the Minnesota Stormwater Manual coming up next. I would like to thank the panelists. I would like to introduce Joanne Boettcher, the Stormwater Research Liaison at the Minnesota Pollution Control Agency. She is going to go over a Minnesota Stormwater Manual tour and resources with regard to media. So she will tell you where to find things in the Stormwater Manual and what is in the Stormwater Manual. Please, Joanne.
Good morning, everyone. I hope you really enjoyed all the information. I am the infant in the room as far as stormwater. I was just in awe. I thought all the presentations and the panel were just excellent. So thank you guys. So I'm the Stormwater Research Liaison and fairly new to my position at the Minnesota Pollution Control Agency. And the first thing I want to mention is that I'm essentially just filling in today for our Stormwater Manual guru. So Mike Trojan, who probably many of you know, retired last month. And we will have a replacement coming on in early June. So in the intermediary, I'm filling in today for this presentation. So forgive any gaps or any issues I have here. So I just kind of want to walk you through a few pieces regarding media. But let me first start with just a little bit of history as far as Mike has relayed to me. So this whole kind of effort with the Minnesota Pollution Control Stormwater Manual is really intended to parallel a lot of the research. My understanding is there's a conversation between Mike Trojan and actually a lot of the folks at the panel today several years ago about we really needed to dig deeper into media issues. And I think out of that, a lot of this research kind of has been born. So the Minnesota Pollution Control Agency some years ago put together a work order with Barr Engineering to scope different media components. And then from there, our agency, probably mostly Mike Trojan, really did a deep dive into literature review regarding media and really focusing on specific applications in stormwater. And in case you're wondering, this is a Queen of the Prairie. So let me first start by getting us to the main page. And I don't need to tell you how to get here because I'm sure you all have this bookmarked already. So if you're familiar with the Minnesota Stormwater Manual, I'll just mention that there's several ways to get places in the manual. probably the easiest way is just to simply search. So here I'm just going to search for media to bring up what we've got for media. And then my search results here pop up. And the first thing here, the soil, media, and media amendments page, I'm going to go ahead and take that. So this page is kind of a bucket, if you will. There is many links to lots of different resources on this page. I'm just going to scroll down until we get to our section on engineered media. So you can see there's a number of topics, and actually I've kind of cut off the few on the bottom there. So there's many topics. And by the way, these links are at the end of this show, and I provided them for the chat as well. So I'm gonna just show us a few different examples here of what we've got. So the first thing I'm gonna look at is the biochar page. So Mike has put together a plethora of information. I think there's about a dozen screens or more. If you scroll down, dozen screens or more of information. And Mike really wanted to respond to some of the needs. We got a lot of feedback about navigability of the stormwater manual being difficult and kind of difficult to understand what was there. So Mike was in his final months here, he was really trying to work to make a few more things straightforward. So he's put in a introductory video kind of going over some of the same information that I'm talking about today. He's provided page summaries in some cases. And this is a really important tool for the stormwater manual, this page content dropdown in the upper right-hand corner. This is essentially a table of contents that links all of the information in a page. So you can just click on that page content, table of contents, click on any of these topics, and it'll bring you right there. So I'm just going to scroll down on this page here. So I just scrolled down to the applications for biochar in stormwater management. I'm not going to go through all this information. Again, this is based on literature review, lots of science and research from folks in the room and others. And of course, you know, this is a continually evolving resource too. So we always try to incorporate new information when it comes out and we feel comfortable with it. I'm going to continue scrolling down to highlight the table we've put together here regarding specific stormwater practices and how biochar can be used, or the benefits of using biochar in those practices. And I'm not going to go on further through those dozen or so pages here. I'm just going to highlight that I just showed you number 1 and 2 from the table of contents, and we've got 3 through 10 still. So if you want to deep dive, the information's there, and then, you know, there's links to all sorts of other resources, so you can go really quite deep if you'd like to. I'm going to back up now to that engineered media page and show you one other resource that is linked to on here. And that is the organic media material properties and specifications. So this table is put together to kind of compare and contrast the different organic media components we've got here. So you can use this to, you know, if you've got a specific design parameter or goal for a project, you can kind of compare and contrast. There's lots of information from anywhere from the phosphorus to safety or handling concerns, physical and hydraulic properties, etc. Scrolling down here, there's a second page of the table, more parameters, research needs. Some of these are a little bit light as maybe we haven't developed all the information yet. And scrolling down to the third page here. And so with that, I'd just like to mention a few of the potential next directions. Again, we've got a new person coming on in June, so these could be retweaked. These are kind of the direction that Mike Trojan left for us, and I think these are good directions, but we'll have to see if those priorities kind of get shuffled around a little bit. But some things we'd like to perhaps develop include more information on layered systems, additional information or kind of tweaking our media mixes. We've kind of, as seen today, we've kind of seen that those have continued to evolve through time, and should our guidance evolve as well. And then more information on vegetation and plant palettes that are different, that are suitable for different applications or different media mixes. And I will note there's a plant selection tool under development right now by Bowser and Metro Blooms. And with that, I'd just like to say thank you for having me, and any questions or comments, I'd be happy to take those.
So questions for Joanne?
Great, thank you.
That's it. Okay, all right, thank you. So the Minnesota Stormwater Manual does have quite a bit on media, and it's building, as you can see, and it's building itself quickly. I'm actually not an expert in the Minnesota Stormwater Manual, becoming more of an expert as I look at it, and there's a lot of information there. So this closes the panel discussion, and it also closes our spring of media discussions. Thank you for attending. I hope it was helpful. Have a nice rest of your day.